very common problem in acid-base is to calculate pHs, pOHs, hydronium, hydroxide of solutions. Well, when you are trying to calculate these answers, the first thing you must always ask yourself is, are you dealing with a strong acid or are you dealing with a weak acid or base? Remember, your data table will tell you this. Don't just try to guess it out. For strong acids, it's just how it was in Chem 20. The concentration of the acid is equivalent to the concentration of hydronium, so you can either be done or you can continue to calculate pH or pOH or what have you. However, for a weak acid, since they do not ionize completely, the concentration of the acid does not equal the concentration of hydronium, which means you need to figure it out. Okay, and if I'm going to figure it out, I can figure it out by using an ice chart. Well, when using an ice chart, I want to use a reaction. This would be the generic reaction you could use for any weak acid scenario. For a weak base, it would look very similar. You could have something like this, where it'd be a negative charge plus water produces the conjugate base and hydroxide. You could use that for a weak base. Okay, so weak acid type of reaction, weak base type of reaction. In this example, we're going to work with hydrocyanic acid, trying to calculate its pH. So, when I'm doing this, I want to set up an ice chart. Now, there will be a shortcut from here, but this is the derivation. The given concentration, so I was told I had a concentration of 0.10 moles per liter. That concentration you will always put in as the initial concentration of your acid. When we're looking for pH or pOH, the equilibrium concentration is what we're looking for. Okay, pH, pOH always refers to the hydronium or hydroxide concentration at equilibrium. The problem is I don't know what it is. I wasn't given anything else but just that value of initial concentration. So, just as an equilibrium unit, when I didn't know what the products were, I wasn't given any information about them, I can assume them to be zero, just like they are here. Well, if I started at 0, I ended at x, that must mean I changed by positive x. And then, just like before, use the ratio to solve for the other change values. Here, the ratio is going to be 1 to 1. That's why this is also a change in x. This ratio is also 1 to 1. So it's also a change in x. But as in the other ice charts, it's a reactant, so it will likely be decreasing. So then I have this value. Those are my equilibrium values for all of my substances. Okay, I have my equilibrium law, products over reactants, H3O times Cn over HCN. But then I have the K value as well. Okay, so I do have a bit of information. I got this right from my data booklet. This is the K value of HCN. Now, put in our values. I've got x times x over 0.1 minus x, and that's no good because it has a quadratic. Well, fortunately, you'll never have to solve a quadratic in Chem 30, so there must be a shortcut. At the bottom of your acid-base table, you'll see a little note referring to an approximation rule. Basically, it says if your K value is so small relative to your concentration, then you can get rid of this minus x term. Okay, and be left with that. With the K value being very small, all that means is that, let's slip back here, if this K value is very small for the reaction, that means I don't get very many products, which means this value of x is going to be super small. And if that is super small, then so is that. So basically, when we subtract, take into account significant digits, that value would still be 0.10. So you get to ignore it, which saves you some grief. So then I can just quickly rearrange this to solve for x, which is going to be the K value times the concentration, and then square rooting it. Don't forget to square root it. And that becomes your hydronium concentration, and then either you're done or you have to solve for pH like we always do. Okay? So, but you do not have to go through this all the time. When you are trying to solve for the pH or POH or hydronium or hydroxide, the approximation rule will always hold, which means you'll never have to solve a quadratic. So when you're going in the direction of solving for pH or hydronium, you can go right into this handy little formula. That's what that ice chart always simplifies into. Okay, if you're trying to solve for a weak base, same thing. But now it's going to be hydroxide, square root of the Kb times the base. And as mentioned before, you'll need the Kw expression to solve for Kb before you do that. Okay, you don't always have to do this, just when you're dealing with weak acids.